In this class, what we're going to do, we're going to take a look at a concept or a topic called the adiabatic flame temperature. And what this is, it is the maximum temperature that you would be able to get in a combustion process. So it enables an engineer to calculate the max temperature that they may encounter for selecting materials or any other thing like that. But it's called adiabatic flame temperature, and just like it sounds, adiabatic means that there's no heat transfer. So we have combustion without heat transfer. That's the hottest that it will be able to get. So that's the idea behind the adiabatic flame temperature. There's no heat loss, so this is a theoretical temperature, and it is the maximum possible flame temperature. So it's a useful number for engineers to use and determine the maximum temperature that they may have in a combustion process. So what we're going to do, we're going to take a look at adiabatic flame temperature for a number of different processes, either steady flow or fixed mass. And we'll begin with steady flow. And in order to do that, what I'll do is I'll write out the first law. So that's the form of the first law. Now we're talking adiabatic flame temperature. Adiabatic means there's no heat transfer, so that's gone. And if we're dealing with steady flow typically does not have any kind of work involved. And consequently, the first law can be recast into just a balance of the enthalpy of the products and the reactants. So that is the equation that we would use if we had a problem involving steady flow and we're trying to find the adiabatic flame temperature. Now for fixed mass systems, what we'll do is we'll begin by looking at constant pressure. So this would be a process whereby you have constant pressure combustion, such as the Brayton cycle was one that we looked at that had that. But we're going to begin by looking at our boundary work. Although for the Brayton that was a steady flow, so it wouldn't apply with this. So we have that for the boundary work, and now what I'll do is I'll write out the first law. So we have that. Now, what we can see, if we look at this equation here, we have the PV term there, and we have the PV term here, and it's it's our specific volume per kilomole multiplied by the number of moles. So that we can make a substitution, and it is equal to the pressure multiplied by the volume of the reactants minus the volume of the products, which we said was the boundary work. And so that enables us to get rid of the boundary work And with that, we can rewrite the equation And so we get that equation if we're dealing with fixed mass, constant pressure. And if you compare that to the equation above, you'll see that these two equations are actually the same. So for steady flow or fixed mass, constant pressure, we get the same result for the equation. So the place where you'd be able to apply this equation, especially one for steady flow, would be gas turbines, such as the Brayton cycle. We said that was a constant pressure combustion process, or a furnace, and that would enable you to get the adiabatic flame temperature. Now, the last thing that we'll look at for a fixed mass is that of constant volume. So writing out our boundary work, for fixed mass we have PdV, but if we say it's constant volume, dV is not changing, so boundary work is 0. Writing out the first law, now we get that for the first law. The first thing that we can do here, adiabatic, so there's no heat transfer, that disappears. Boundary work we just said was 0 with this, so that disappears as well. Now we have this PV term here, which isn't the easiest to deal with, and we like to have another way to deal with that because it's hard to measure specific volume on a per kilomole basis. It's easy to measure pressure, but not specific volume per kilomole. So what we're going to do, we're going to use the ideal gas equation in order to kind of clean up that formulation. And if we look at the ideal gas equation on a per mole basis, we have this. We divide through by the number of moles, and what we get is specific volume per kilomole is equal to RUT. And RUT is something we can easily measure temperature, and so we can plug it into that equation and clean it up a little bit. So let's do that. So that is the equation that we end up with for the adiabatic flame temperature when we're dealing with fixed mass, constant volume. Applications of this equation. One place that you could use it is heat addition in the ideal Otto power cycle. where there we had a constant volume heat addition process. So that gives you an example of how to calculate the adiabatic flame temperature, be it a steady flow, fixed mass constant pressure, or fixed mass constant volume. What we'll do in the next couple of segments is we're going to work an example problem enabling us to apply the idea of adiabatic flame temperature to a specific problem.